Okay, everyone. The third thing I'd like to do today is to introduce the Taylor series expansion. This is a mathematical way to approximate a complicated function, usually in terms of a much simpler function. And it can be really useful, all right? And it will be useful in our class. One of the reasons I'm introducing it here. Okay, here's what the Taylor series expansion does. If I have some function, f of x, and I know its value at one point, let's call it x0, it allows me to find a simple approximate formula for the value of the function at some other point, x, where x has to be nearby the point x0. Okay? Let's see how this works. So we can find the value of f at position x from the values of f of x and all of its derivatives. The first derivative, which I'll call x of x, f of x prime, f prime of x, f double prime of x, that's the second derivative, and so on, okay? And we assume that we know these values at some reference point, x0. And starting from there, we can extrapolate to find the value at x. And here's the result. F of x is equal to f of x0 plus x minus x0 times the first derivative of f with respect to x, evaluated at x0, plus 1 over 2 factorial, which is of course just 1 over 2, times x minus x0 squared times the second derivative of f with respect to x0 plus 1 over 3 factorial times x minus x0 cubed times the third derivative of x minus x0. Oh, excuse me. Evaluated at x0. Sorry for my confusion here. Plus, and then the series continues. And what's useful about this, well, this is always true, but it's useful if x minus x0 is a small quantity, if we're close to the reference point. Because in that case, each of these terms gets smaller than the preceding terms, and we can usually terminate this series after the first couple of terms, or maybe even after the first and second term. Here's an example. Here's a fairly simple formula. F is equal to 1 divided by 1 plus x. Okay? And suppose we want to evaluate this near the point x equals 0. Okay? And we want to be close by so that x is much, much less than 1. Okay? Well, normally we'd have to use a calculator to evaluate this. And the result is kind of messy. So it'd be nice to have a simpler approximate expression. Okay? Well, to do this, we only need to work a few things out. First, the first derivative of f with respect to x is, of course, minus 1 divided by 1 plus x squared, okay? And the second derivative is 2 divided by 1 plus x cubed. Oh, I'm sorry, I'm put that in the wrong place here. There we are. And well, and so on, but we won't keep any more terms than that. Then f of x can be written as 1 over 1 plus x0 minus x0 times 1 over 1 minus x0 squared okay, plus 1/2 of x minus x0 squared times 2 divided by 1 plus x0 cubed, and so on. Okay? In our case, we made x0 equal to 0, so that f of x is equal to 1 over 1 plus 0, or 1, minus x times 1 plus x squared times 1. And then the next term would be x cubed. And in fact, we have the harmonic series here, which you may remember is equal to 1 over 1 plus x. Okay? But really here, I'm interested in this result. So that's the series, but in the limit that x is much, much less than 1, each of these terms becomes much smaller than the preceding term, and we can say that f of x is approximately equal to 1 minus x, so that 1 over 1 plus x is approximately equal to 1 minus x for x much, much less than 1. And that's so simple that it's a useful result. Okay? All right, well, that's an example of the Taylor series. Okay? Here are the rules for calculating the Taylor series of expansion for any function that you like. And then we've illustrated it with this function, one of the most useful applications of it. All right? And there's one or two other cases that will be interested in our course, and they're going to come up right away, which is why I introduced this today. So I hope that all made sense, and I'll see you in class.